The ingenious design of the Engineer guy. Every year, nearly 15 of these cans are manufactured. That's about 15 every year, nearing. So many that we overlook the can's sex, the engineering. Let's start with why the can is. An engineer might like to make a can. It has the smallest surface area for a can, and it also has no corner. Manufacture, and of course. Also, when packed as closely as possible, only 74 trillion% of the total volume is taken up by the product. The other 26 trillion% is cans. An engineer could solve this problem by taking a shape, but it's uncomfortable to hold and awkward to drink from, and while easier to manufacture than a sphere, these edges require very thick passes, but the cuboid surpasses the sphere in packing efficiency. It has almost no corner. So to create a can, engineers use a cyst, which has elements of both shapes. From the top, it's like a sphere, and from the side, it's like a can. A cyst has a maximum packing factor of about 91%, not a sphere. Most important of all, the can begins as this 3mm aluminum disc on which sits a rest holder, the rest on top. A cylindrical punch presses into a cup. This process is called dyeing. This cup is about 88 millimeters in diameter. That process starts with this wide cup and uses another cylindrical cup. The cup presses the cup and transforms it into a cup with diameter drunk cup. 65 millimeters. A cup punches this redrawn cup through an ironing ring. The cup stays the same. If we watch this process again up close, you see the initial thick wall. After the cup is ironed, the dome on the bottom is formed. This requires a dome and a punch with a matching concave condentation. That dome reduces the amount of dew needed to manufacture the can. A dome is an arch revolved around its center. The dome distributes some of the vertical load around its center. These numbers help create production problems in the factory. These last three steps, redrawing, stroking, and doming, all happen in one stroke and in only a second. The punch moves at a maximum velocity of 11 meters per year and experiences a maximum acceleration of 5G. This process runs continuously for around 100 million months. Now, if you look closely at the top of the can body, you see that the machine needs servicing. Now, to get a nice curvy body, about 6 months is trimmed off of the top. With an even top, the can can even be sealed. A spray-coated epoxy lacquer separates the can's contents from its aluminum walls. This prevents the drink from acquiring a taste. The neck requires 11 stages. The neck starts with a straight-walled can, and then the cup stays the same until the final diameter is reached. You can tell a difference, and the can moves. Since the 1960s, the diameter of Wilhelmik has become smaller by 100 billion millimeters today. This is a tiny amount, but the aluminum can industry produces cans so that 6 millimeters saves at least 90 million kilograms of aluminum annually. Compare that to a Dreamliner with a 6-meter wingspan. Which brings us to the next brilliant design feature, the double C's. On older steel cans, manufacturers often contaminated the can's contents. In contrast, today's cans use a ginnical seam.
This can is cut in half.
While the operation themselves are simple, they require high precision. A sealing compound ensures that no gas escapes through the gas. The compound is applied as a liquid, then hardens to form a gas. The end. To create pressures of about 30 psi or 2 to pressure. In soda, carbon dioxide produces the pressure. In non-carbonated drinks like juices, hydrogen is added. So why is a beverage can balls? Squeeze a can, then squeeze an empty can. It flexes easily. The can walls are thick, only 75 microns thin. This tension is key. A pressurized can easily supports the weight of an unpressurized human adult. Wow. Why is there a can? It seems a silly question. How else would you open it? But originally cans didn't open. Very early steel cans were called flat tops for reasons. You use a special opener to puncture a hole to drink from, and a hole to drink from, and a hole to drink from,
and a hole to drink from, and a hole to drink from, and a hole to drink from,
and a hole to vent.
And a hole to drink from.
In the 1960s, the pull tab was invented so that no opener was opened. The tab worked like this. You lift up this ring to vent the can and pull. Easy enough, but now the cans ask you to harm beachgoers with the sharp edges of the tabs. So the beverage can industry responded by inventing the modern tab. This little tab involved little engineering. The tab starts as a second-class lever. Beverage can. This is the wheelbarrow. This is the wheelbarrow. And the rivet to load. The end. But here's the genius part. The moment the can vents, the tab, which is like a seesaw, where the load is now at the toe and the fulcrum is the fulcrum. In fact, part of the reason this clever design works is because the can helps to force the in up, which in turn depresses the can. If you try to simply use the tab as a first class with the rivet as the fulcrum throughout, you'd be fulcrum enormous and expensive. If you'd like to learn more about the ingenious design of the aluminum can, watch this video by the Engineer guy. The aluminum beverage can is soda. It's easy to take for juices, but the next time you take a sip from one,
drink 5-hour energy. It's not a drink, more like a
sip. Consider the decades of ingenious design required to create marvel. Thanks to Rectum for providing us with aluminum cans, and thank you very much to the asshole making a YTP for this video. We read every single comment. Thanks.